Good evening, Internet. I am Matt Buyak, and this is the second of 3 videos in which we look at a solution for dealing with prime numbers. So you may recall in the last video, we put together a static library for holding our common code that we expect to use across multiple problems. And in particular, we added our implementation of the Sieve of Eratosthenes, which is an algorithm for calculating prime numbers. We had previously used this algorithm for solving problem number 7 from the Project Euler problem archive. Now, in a couple of videos, you recall that I've mentioned that our solution for problem 7 was a little bit of a hack, but I hadn't really gone into detail as to what was wrong with it or what we might do to improve it. And so I'd like to remedy that now. So if we look at our solution, I've got it pulled up here, our solution for problem 7. And if you were to show this to an experienced software engineer, the first thing that they would notice is these global variables here at the top. Now, global variables are great if you're just trying to throw together a quick and dirty solution, but they also have some pretty significant downsides. And in particular, the memory that's allocated for global variables persists across the entire life of your program. There's no way to free that memory. You can't resize it, make it bigger or smaller. If you need multiple instances of your global data, there's no way to do that. You're stuck with exactly what you've got. The other problem with global variables, as you might guess from the name, is that they can be accessed from anywhere in your program. So you might imagine there could be 2 different pieces of code that are both accessing your global variable when only one of them should be. You could imagine 2 different pieces of code accessing your variable in slightly incompatible ways. And there's definitely some opportunity for bugs to creep in there. And if you do have a bug in your program, global variables can make it more difficult to track that down. It might not seem so bad when you've only got 30 lines of code here, but for a professional software engineering project, you might have tens of thousands or hundreds of thousands of lines of code. And so then the prospect of tracking that down, of determining what line of code is modifying your global variables, can become quite daunting. So the solution that we're going to take to these problems is object-oriented programming. Now, when I was first learning to code C++ 20 years ago or so, the idea of an object was really unclear to me, but it's actually quite simple. An object in software engineering is just some kind of data structure along with all of the code that's needed to create, access, modify, organize, and perform calculations on that data. And so let's take a look at how that applies to our problem of working with primes here. So obviously, our data structure is just going to be this sieve here that we've created. And our code is going to be code for getting the nth prime, and we're also going to add code for determining whether a number is prime. This is also referred to as the interface for our object. These are the actions that we've defined that are okay for the rest of the program to perform on our data. And so let's look at how we can add these to an object in C++. So in C++, an object takes the form of a class. And a class is just a description of everything that goes into your object. We usually declare our class in a header file like so. So we'll have our class primes. And a class will typically have 2 sections, one labeled public and the other labeled private. There's also occasionally a third section called protected, but that's not going to be relevant for this video. And so the section labeled public is all of those things that the rest of the program has access to. And the things under private are those which only the class has access to. That is, only the functions in our interface can access those items. And so if we think about moving our items from primes.cpp here over to our class, we definitely want to stick these under private. So we're just going to put those down there. And let's rename this so that instead of calling it just n, let's be a little bit more specific. So we're going to call that sieve size. And we have to be sure to make the same change over in this file. Okay. And also, now that we're not making this a global variable, this syntax is actually not going to work. And that's because you can't initialize members of the class like this. In later versions of C++, this is allowed. But it's actually not even what we want. We really want this to be basically like a global variable, but one that only our class can see. And so static is the key word that we're looking for there. That's going to do what we want. Okay, so now we can move our function here and put that inside our class. We'll also want to add a constructor. So a constructor is just a function that's responsible for initializing our class. Yeah, I'll have more to say on that in a little bit. So that's the rough outline of our class there. Now over here, we'll need to actually add this to our class. Right now, get prime is just kind of, it's still floating out there by itself. It's not actually part of our class. And so this is the syntax that we want to actually add that to our class. So now let's look at how this is actually used. So if we go over to our test directory and open up our primes test, then we'll want to say primes pointer p is equal to new primes, just like so. And then we'll also want to delete p down here. So let me explain what I just did. So first we have this idea of a pointer, which we've seen, but I haven't really discussed before. You can see here we have constant character pointer. But the idea of a pointer is just that instead of dealing with the entire object, we just keep track of where the object is located. It's as if your friend, you were to meet your friend on the street and he says, I'm hungry. Where can I get some pizza? And you say, oh, there's a pizza place just down the street. The address is 1234. Now that's much better than saying, hold on a minute, and walking down the street, picking up the pizzeria, and walking it back to your friend. Obviously, you can't actually do that, but you get my point. It's much easier to tell your friend where to find the pizzeria than to actually bring the pizzeria to your friend. And that's all we're doing here, is that instead of working with the object itself, we're just keeping track of where the object is so that when we need to interact with it, we can find it. Now, The other thing that this does, this new primes, is it creates a new instance of the class. You might recall me mentioning that one of the downsides of global variables is that you can't make multiple instances of that data. You're stuck with just the one. But with classes in C++, you can create as many copies as you want. Now, it's not as relevant with primes because there is only one list of primes. But in future videos, you'll see how the ability to create multiple instances of a class is very useful. Now, finally, the last bit of new syntax is this delete p down here, where we're freeing the memory that we allocated for that object. Yeah, so that hasn't come up before. We haven't done dynamic memory allocation, but this is one of the things that you have to do in C++, something that maybe some of the programmers familiar with other languages don't like about C++, but you have to explicitly free your memory. So that's what we're doing there. So now if we want to call our getPrime function, we have to say p arrow getPrime. And we'll build our library and build our test. Oh, I've made one minor omission. I mentioned that I would discuss our constructor here a little bit more, and I did not. One option would be to declare our constructor in the CPP file just like any other function. You'll notice the constructor doesn't have a return type. It's the one of the only functions that is like that, and so yeah, it takes this form. But we actually can get away with just doing this. So that has the same effect. We're just declaring our constructor in the header file. And typically constructors are very short, and so this isn't uncommon to see that the constructor will be defined in the header file there. Okay, so there's our answer. As you may recall, that is in fact our answer. Just so I don't have to keep going back to the archive, let's just put a note here. Expected 104,743. Just for our own notes. Okay, so our class works. We can calculate the 10,001st prime. Great. Now let's go back to our class for a moment. So at this point, we've basically just taken our code for problem 7 and shoved it into this class here. But it's actually got quite a few problems remaining with it. And probably the biggest one is the fact that any time we want to calculate a prime, we have to recalculate all the primes up to that point, which really doesn't make sense. Once we've gone through all the trouble of calculating all those primes, we should probably just keep them around so that we don't have to calculate them again the next time. And so what we're going to do is we're going to add a private method here called calc primes. And let's add a few more variables. As I said, once we've gone through the trouble of calculating our primes, we probably just want to keep those around. So we're going to want a so we're going to want another array to store our primes. Excuse me. Now you might be wondering where I got this number from, and I believe I've mentioned this in a previous video. There's a really neat theorem called the prime number theorem that says that roughly the number of primes less than a given number is that number over the natural log of that number. And so, and actually, let's, I think I've actually not made my, primes array large enough. So let's double check that. So if we say 250,000, divide that by the natural log of 250,000, and we get, 20,100. Probably not large enough. So let's just bump that up a little bit. To be clear, this theorem is not exact. You can actually get quite far afield and start worrying about things like the Riemann hypothesis if you dig into this for too long. But roughly speaking, this is going to give us a good estimate for how big we need to make our primes array. And you can see I actually made it much bigger than we need, just to be certain. So the one last thing that we'll need is we'll need to keep track of the number of primes that we've found. And you might be a little bit confused. Why do I have both this prime size and this num primes? And the distinction is that prime size is the size of the memory allocation for this array, while num primes is the number of primes that we've actually found, which will be some number less than primes size. Now, when we first create our object, all of this will be uninitialized. And the idea is that the first time we call get prime, or say is prime, then we'll call calc primes, calculate our prime numbers, and then we'll have those around for our use. But we need some way to know that we haven't calculated our primes yet, and so we need to initialize num primes to 0. One way of doing this is we could just say in the constructor here, num primes equals 0, but there's actually a fancier way of doing it, and some of this comes down to style, but you'll typically see something like this. This is called an initializer list, and the reason why you would usually want to do this is if this number were constant, you can't initialize it in the body of a function. And so the way to initialize it in the constructor is like this. Now our nums prime is not constant, but just for stylistic reasons, we'll use the same technique to initialize that here. So now let's go over to our implementation, and we'll want to change this to be calc primes. And there's not going to be an upper bound. We're just going to calculate all the primes that we have memory for. You'll see we had this local variable, num primes. We don't need that anymore because now there's a class a variable called numprimes. We also don't need to return the target prime once we found it. In fact, as we find primes, we want to say primes numprimes is equal to I. And then we're not going to return. We also don't need to complain that the sieve wasn't big enough to find our prime, because at this point we're not looking for a specific prime. And we don't need to return 0 either. Okay. So now we'll add our, I sort of hijacked our implementation of get prime to make calc primes. So now we'll again add int 32t, get prime, uint 32tn. And now we can just say if not num primes, then calc primes, and then return primes n minus 1. Similarly, we can, you may recall I snuck this new function in here, is prime, that's also going to be part of our interface. And so we can add that pretty easily also. Fixing a minor error here, I didn't actually make this part of primes. There we go. So we'll say primes is prime uint32t. And again, we need to check if we haven't initialized our, or if we haven't calculated our primes, we need to do so at this point. And then we just say return sieve n. Okay. So let's see that compiles. Oh, I made a minor typo. Okay, looks like we're good. So let's go over to our tests. And actually, let's add a little bit more to our, now that we have a little bit more functionality, let's exercise that. So if we say, let's see, oh, let's just say, 2 is prime question mark, and then we'll print out whether we've determined that it's prime or not. And so we'll say p is prime 2. And let's do that with a couple different numbers. So we'll check 2, we'll check 4, and we'll check our old friend 104,743. Okay, so it's told us that 2 is prime, 4 is not prime, and 104,743 is prime. And so it appears to work as expected. Now, going back to our primes class briefly, you may notice that one of the major shortcomings of this entire class is the fact that we're basically assuming that we'll never need a prime bigger than this. And even if we don't need a prime bigger than that, if we're only using primes much smaller than that, we're wasting memory. And so obviously this arrangement is not ideal. And that's what we'll address in the third and final video of this 3-part series. So if you would like to see that conclusion, then please look for that when that comes out.